today I'm going to cover an introduction to the DNP3 communications protocol and its use with the FB3000. And the important thing to realize, the reason we're doing this is because we position DNP3 as our primary protocol for the new RTU moving forward. And obviously, we want all of our customers and users to understand a little bit why we did that and how to use it. So the first question is, what is DNP3? Well, it's the short phrase DNP3 means Distributed Network Protocol version 3. And it's basically a standard defined by the IEEE and also the IEC, introduced in 1993 with the last major update in 2012. It's been used very widely in the electrical industry, and they adopted it to give compatibility between a very wide range of different equipment and reliability. We're going to discuss some of the advantages as we move forward. The important thing is it allows automation systems to transfer data between masters, which are equivalent to SCADA servers, and outstations, which are RTUs. It also allows, which has been very useful for us as we move forward, vendors to expand the protocol, add some new features, and to transfer files between systems. So that's the quick, what is DNP3? We'll now dive a little deeper. Why, as customers, would you choose DNP3, and why would Emerson as a vendor use it as the protocol for our new RTU? The primary reason is it can reduce costs, project timescales, and also reduce risks. The first reason it does this is it's very, very standard, highly standardized. It's a non-proprietary protocol, and it's well documented. That's compared to Modbus, where you see multiple variations all over the place. And this standardization means that when you combine products from different vendors, there's very little risk. There's also a very wide adoption across different vendors, which provides you as customers with choice. It gives us increased competition, and obviously that overall reduced costs. One thing that's interesting, compared to Modbus and some other protocols, it actually defines standard data types called variations. We're going to talk about those today, but the important thing is you're no longer in a world where you wonder what kind of floating point value you're using or what order the bits are in an integer. And it obviously also defines the communications protocol as well. And this push for standardization is so important that the DNP3 user group, who lead and direct the standard, organize regular plug fests. And you can see one here in Europe. Customers turn up, they bring their equipment, they plug it all together and check everything from different vendors works together. Also, as someone who's trying to implement systems using the FB3000 or using DNP3, there's a lot of resources out there on the internet, both commercial, free resources, other companies, and tools that allow you to build and diagnose DNP3-based systems. There are also independent testing labs who will test any piece of equipment to determine that it conforms to the standard. So all of those give you complete standardization compared to either Modbus or proprietary protocols. Also, in the business we're in, scalability and performance are highly important. The protocol includes event-driven reporting, so data changes are detected and then they can be transmitted by exception. It's extremely reliable. The electrical industry, like the oil and gas industry, deals with a lot of poor quality, low bandwidth networks. There's a lot of features in the framing to deal with that. It also supports extremely large networks and also has a very large internal address space per device. Now, obviously, that's limited by the resources and the memory on whatever hardware you're using, but what it means is DNP3 is pretty much future-proofed looking forward in terms of the amount of data it can handle. Finally, cybersecurity is something that interests us all today. DNP3 provides something called secure authentication, which is a mechanism where a DNP3 master, that's a server talking to an RTU, can be confident that they're both talking to authenticated, genuine devices that are authorized to be on that network. That makes the introduction of either rogue equipment or malware into the network very difficult. And Emerson's going to be working in the future to add these features to all our products. We've started with the control waves and Open Enterprise. Moving on, let's take a look at what a DNP3 network looks like. You can see the diagram there. It's fairly traditional. We have a DNP3 master at the top of the network and multiple outstations. You must always have at least one master and one outstation in any network. Physical networks that are supported by DNP3 are all the traditional ones we have in the automation industry, including RS-232, 485, Ethernet, lease line, optical fiber, radio. Really, if you can communicate a signal over it, DNP3 supports it. It should be noted that on a serial link, DNP3 is the native protocol, so that's the protocol you'd be using. It also can be supported over TCP and over UDP IP. To address outstations, use a simple 2-byte integer, which in theory gives you up to about 65,000 addresses. Actually, 16 of those addresses are reserved for future use and also for broadcast messages. You can send some messages to every device in the network at the same time. Open Enterprise and most competing SCADA platforms are DNP3 masters, and our range of hardware, FB1000, FB2000 flow computers, the FB3000 RTU, and the control wave platform are all DNP3 outstations. So if you take the generic DNP3 network, this is what it looks like if you use an Emerson solution. Open Enterprise at the top and the various Emerson hardware products below it. One thing I'll mention here, I'm already using some DNP3 terminology. I'm going to use the word outstation, which is what the electrical industry and DNP3 uses, and the word RTU interchangeably throughout the presentation. I'm trying to use it where it's appropriate, but the two terms are interchangeable. So that explains how the network works. What happens inside the RTU? Just like using BSAP or just like using Modbus, there's the concepts of inputs and outputs and signals, but it's slightly different terminology. A DNP3 point is the equivalent of a signal, a tag, a coil, or a register. It's really the smallest item we're dealing with that holds data. Almost all DNP3 communications are based around the concept of either writing or reading those points. Within the DNP3 world, an input is something that's normally driven by changes either in or at the RTU. So for example, a pressure might change or you might read a different flow. An output is normally something that's written to the RTU from a DNP3 master. And it's important to realize it's not necessarily a physical I/O point. It can be a pseudo point. And a pseudo point is a point that doesn't have associated I/O, but it exists in RTU software. So for example, it might be a PID set point, the value of a timeout, an alarm limit, perhaps a configuration point, or even the clock. With DNP3, it's possible to read and write to both inputs and outputs, but it obviously depends on the functionality of the individual DNP3 point, whether that makes sense. And the important thing to realize is all DNP3 outstations and masters must support DNP3 points. So, of course, the FB3000 support DNP3 points. There's multiple different types of point, and these are referred to as DNP3 point types. So every point that's created must have a specific type. So for example, it might be a digital input, it might be an analog output, or it might be a digital output. Those point types are defined by the standard. So you know if you're, for example, collecting a binary input, the exact format of that data, how it's defined, and it's in the specification, the DNP3 specification from the IEEE. Now, I'm not going to go through all the point types here, but this table shows all the point types that exist and are defined by the DNP3 standard, and then those X's over in the right-hand column, those are the ones that are used and supported in the FB3000. And those are the ones that if you're using the product or you're configuring a SCADA system to talk to it, you'll need to be familiar with. realistically, it's the analog inputs and outputs, the counters, and the binary inputs and outputs that will be of most interest, but I have listed them all here. So I've identified what a DNP3 point is. I've explained that there's different types of DNP3 points. How do you actually determine which point you're accessing? To do that, you use a DNP3 point index. And it's pretty simple. There's an integer number that must always start at 0 that identifies each individual point of a type. So it's important to realize that, for example, those integer indexes are unique to the type. So, for example, you can have a digital input 0 or a digital output 0. Those are separate points. They're not connected or associated in any way. It's just they've both got address 0, but you also need to indicate which point type you're talking to. Now, the indexes on an FB3000 are 16-bit, so in theory, you could have over 65,000 points of any type. But there's obviously internal limits based on the amount of memory in the device. And at the moment, those are listed in the product documentation. I've included it in this table for convenience. So, for example, we support up to 4,100 DNP3 analog outputs. I'd recommend that you always check the documentation. Those numbers may increase in future releases of the firmware or the product. Now, having then identified what the indexes are and how you access a point, how do you make it so you can access points with the device itself? Okay. Now, with those of you who've used the FB3000 or the flow computer may be aware that there's an internal database, and that database contains parameters. We also call them tags. So, for example, there may be the flow for meter 1. Each of those parameters within our software, that's typically the FBX Connect software, is normally referred to by a unique name. So, for example, that might be DI1.1, that's the first input, card 1.selected. If you're communicating with the device using DNP3, you need to map that into a point type with a point index. So you can identify it via the DNP3 protocol. And there's two ways we can do that with the FB3000. The first way, which is the easiest and very simple, the product comes with what we call the default map, a standard map, which is basically a list of points, a list of tags, and their addresses with the index and the point type. Or you can create a user-defined map. Some people call this the custom map. So you create your own map and use it instead of the default map. To create that map, use FBX Connect, which is the configuration tool. It's actually part of Field Tools. And you use the DNP3 map table register window. And I've actually got a screen capture of it here down the bottom right of the slide. Use that tool to select a database parameter and then map it to a point index and a point type. It's pretty easy. I don't know if you can see the mouse here. You choose the point type here, you choose your parameter from the database here, and then the point index is here. So in this example, if you look carefully, you'll see that the fourth input on digital input 1, digital input card 1, selected, that parameter, is mapped to binary input number 4. And at this point, you might look carefully and notice that it actually says 5 by that. Something I need to point out, I noticed last week, there's a minor bug in the current version of the tools, that those indexes in that window are offset by 1. I've already spoken to the development team. That will be fixed in the next release, but just bear it in mind if you're using this tool. But very simply, you use this tool to associate a database parameter with a point index and a point type. You will also notice over on the right that there's something called a class and a variation you associate with each parameter. We're going to talk about that later in the presentation today. That's how you do a custom map. If you decide not to do that and you just use the free included DNP3 standard map, that's included in documentation. So there's a manual I've got an extract of it there, and if you have a look, that's the document number. I've got these as references at the end of the presentation. That lists each point index, the standard parameters, and how they're mapped. Obviously, not every single parameter within the RTU can fit into the DNP3 map. So what we've done is we've selected the most common ones for approximately 24 meters, and those are all mapped and documented. And one thing I wanted to point out is in the documentation, the point indexes are correct. You'll notice that it begins with a 0. One thing I should point out, though, you have a choice. You either use the default map, as shown in the documentation on this slide, or you use the user-defined map. You cannot have both concurrently in operation. And the user-defined map starts empty. You get the opportunity to create your own map from the beginning and create exactly what you need for your application. And obviously, I would recommend that you probably use the same map for each of the devices, each of the RTUs in your network. So you, for example, have a standard point index for a particular parameter across all of your devices. So moving on from the mapping, how do you determine the different types of point values? And let me explain what you mean here. This is actually DNP3 terminology. In Modbus, you often refer to, say, a real-time value. With DNP3, what we've referred to as a DNP3 static value is actually real-time. This is a little confusing. The static value is the value of a point at the current time. It's definitely not static. I don't know why the DNP3 guys called it that. It will change as the IO values change or the points written to or a counter increments. But try and remember that as we move through the next slides. The static value is your real-time value. An event or an event object, this is the value of that static point at some time in the past. So normally it'll have a timestamp, though that's actually optional in the standard, and it's effectively an entry in the historical log for the point. And it's captured normally as the change in value is detected. And we're going to go into events a little more on the next few slides. Finally, the third type of value, which you'll see in the DNP3 documentation, is a frozen value. DNP3 has the concept where you can take a bunch of points and freeze them or snapshot them at a point in time. So you might say at this instant, snapshot all those values across a meter, and those will be held and frozen. However, the actual real-time value, the static value, isn't frozen. It will keep on moving, but you can make a request for what you froze. The idea here is that you can freeze those values and then make a request for them later, perhaps while you're investigating a problem. Now, this feature is in our future plans for the FB3000. You will actually see it in the documentation, and it's mentioned in a few places in the user interface as FBX Connect, but it isn't yet functional. I've shown it in gray there. That's a future feature, but it is a standard part of the DNP3 protocol, and it's mentioned in the documentation. So I mentioned it here. Moving on, I want to talk a little bit more about events. Okay. In general, generally the inputs of the DNP3 point types support this internal historical logging of change, and they're referred to as events. Most of those support both static and event data access, and as I mentioned on the last slide, the static value is the current value, the real-time value, and that's the value at the time when you make a DNP3 request, whereas the event data is always the data at some previous point in time. As the current value of parameters changes in the FB3000 database, optionally you can configure the RTU to create DNP3 events, and those can be buffered and then collected by your DNP3 master later. This is a lot more efficient because what it means is the SCADA system can come along and just request details of the changes that have occurred in the internal database. You don't need to poll every 5 seconds to get data with a 5-second resolution. Even better than that, the FB3000 has the ability to send those events to the master by exception, so they only get sent. You don't even need to request them from the master. And the events are therefore very powerful. They combine the concept of historical data and report by exception. Report by exception is a feature that you may have been familiar with the BSAP and the ROC protocols. It's something that Modbus does not have as a concept. So a little diagram of how this works. Let's imagine we've got 3 analog inputs with those values, point index 0, 1, and 2. We'll then have some event data, perhaps logged, and if you look, that goes from 8 o'clock in the morning through to 10 o'clock, and we've got 6 events logged, each with their own timestamp and a point index. And what's happened is, over time, that first point, 0, changed at 8 o'clock, it changed at 9 o'clock, it changed at 10 o'clock. And you'll also notice that the event value for the 10 o'clock matches the current static value because it's the most recent change. Same for point index 1, there was just a couple of changes there. And then we can see that point index 2 changed just once, 8:15. So when a SCADA system comes along, it can request either the event data or it can request the static data. And if it requests the event data, it gets a historical view of what's been happening in that RTU, and it doesn't need to poll all the time to get data, even though it's over several hours. One thing we haven't talked about is how you determine which action. I just mentioned there that you could request the static data or you could request the event data. DNP3 groups are how you define those actions. And this is confusing. The yellow box, pay attention to it. The name group is more than just a group of points. In fact, it's an action that can be performed on points of a certain type. And I'll explain it here. There are multiple groups that are defined per point type. So remember, a point type is, say, an analog input. A group is defined as an integer number. So, for example, I may say this is group 3. Each group defines the actions that can be taken only with the points of an associated point type. And there's a fixed, predefined range for every point type. These actions are fully defined by the standard. Manufacturers cannot add their own options or change them. This gives a great deal of interoperability or compatibility between devices because you know what a device is going to do when you use one of these groups. And it's very important to realize that a group number, for example, 50, only ever applies to a single point type. So it effectively specifies a point type as well. As a simple example, analog inputs are defined in the standard as having groups 30 to 39. In fact, here the list it. So we've got groups 30 through 39. So let's say I wanted to read the static real-time value of an analog input. I use group 30, and that will give me the analog input value with some quality flags. Similarly, group 32 will read all the events for the point with the flags. You'll also notice that I've put a little X there showing which ones are supported in the FB3000. It isn't necessary for an outstation to support all of the actions, all of the groups, but you must define the ones you do support, and we'll have a slide on that later. All of the groups we support are documented in our product manuals. In fact, in the protocol specification manual, I've included a screen capture there, and you can see them listed. So to summarize this, group 30, for example, performed on point ID 5, means read the current value of analog input 5. We're going to come back to that, to the refresher, but so really by specifying just the group number and the point ID 5, that tells the RTU we would like to read the current value, the static value of analog input number 5. One thing I've not discussed, but anyone who's familiar with Modbus is familiar, Modbus has many different ways of representing values. So, for example, you might have a floating point, you might have an integer, a signed integer, a 64-bit integer, and then there's a lot of complications with the different order of bytes and so on. And every Modbus communication setup I've ever done, we've had problems with them, especially from different manufacturers, because there's no real standard. DNP3 has a huge advantage. All the different formats for data are defined as part of a standard, and they're referred to as variations. And for every DNP3 group, there's a number of standard variations defined, and you use those to state the format you would like to put the data into. So if we go back to analog inputs again, I've already mentioned that the FB3000 supports groups 30 and 32, and you can see here that we've got 6 variations for group 30. So when we do group 30, we are reading the static value, that's the real-time value, and if we say wanted to read that as a double, we say we want variation 6. But let's say we want it as a 16-bit integer with some flags, we use variation 2. Similarly, we can go to group 2 to read the events, and there we've got the same options for different formats for the data we return. And because all outstations use the same variants and all masters, DNP3 masters use the same variant, there should never be any confusion as to the data you're getting back. Also, something Modbus can't do, you can bring the same data back in different formats depending on what you want to do with it or what your software requires. Normally, the DNP3 master, when it's requesting data, will always specify one of the variations. Makes sense. It defines what data it wants. However, it can also request what we refer to as a default variation, variation 0. You'll notice that there is no 0 in the table above. The reason for that is because within the RTU, when you map a point, you can assign it a default variation, which is one of the variations shown on this table. And you may have noticed, if we went back a couple of slides, that screen capture of the documentation showed you choosing a variation for each point. And when the master requests variation 0, the RTU gets to decide the format that's returned, and it will be the default. Those variations I've mentioned are defined either in the default map in the documentation, or when you're using the FBX Connect configuration tool to do the mapping, you can choose them there. So I'm going to summarize here. To fully define a read or write action for a DNP3 point, we basically specify 3 integers: the group to specify the point type and the action, the point index to identify which point within that group, and the variation, which defines the format of the data to be written. And those 3 integers are common to every implementation of DNP3 and standardized, though obviously the index will give you a different point depending on the configuration of the device. So once again, I'm going to summarize this, go through it again as sort of a worked example. I already mentioned there are 3 things we need: the group, the point index, and the variation. So let's say I would like to read the current real-time value of differential pressure, first meter in the R2 energy rate, and we want it as a single precision floating point value with quality flags. That indicates if there's an I/O failure or comms failure with flags. So we are using the default map that comes with the FB3000, so we need to have a look in the product documentation, which I've included a copy of on the right. So the first question we should ask ourselves, what kind of point is it? Well, this is clearly an analog input. Which group is used to read analog inputs? And if you look in the documentation, the real-time value for analog inputs, that's the static value, is group 30. We wanted to read it as a single precision value, so which variation is that? That's variation 5. And we wanted to read that particular energy rate, so which point ID? And again, that's included in the protocol manual. You'll see it's point 49, the number 49. So the read 30, 5, and 49, those 3 numbers tell us exactly what point which to access and what function we're trying to achieve. So it's actually quite simple when you put it together like that. However, you will also recall I mentioned something called classes earlier. And this is a more efficient way of reading data. If you think about it, I have to provide 3 integers to get to each point, the way I've just described. You can actually assign each point to a class. And that class determines how data is moved from the real-time values over into the events. The actual functionality of how that occurs is manufacturer dependent. DNP3 doesn't specify it. All it says is there has to be 4 classes and they're numbered through 0, 1, 2, and 3. Class 0 always refers to static data, to the real-time data. So when a DNP3 master requests class 0 data from an RTU, the RTU reports back the most recent value for every single DNP3 point that's mapped to DNP3. So it sends back the real-time value and the flags for every single point in the map. You can see that you can use that to determine the configuration of the device because you have a list of all the points. For those of you who've used BSAP, in some ways this is similar to the SIG file that we used to have for a control wave. Also, you can use it to read all the current values, though it's not that efficient to do that because you're obviously reading every single value from the RTU, but it's something you may do when you're initializing communications to a device before you start looking at events. Every single parameter that's mapped to a DNP3 point in the FB3000 automatically exists in class 0. Also, in the FB3000, it's optional that you can map it to either any one of class 1, 2, or 3, or to all of them. So it can either be 1, 2, and 3, or 1, 2, or 3. That makes sense. You can't put it in just 1 and 2. Classes 1, 2, and 3 are event classes. As I've just mentioned, DNP3 does not define how the events are generated, only how they're formatted, which is using the variations. Different products and different manufacturers can do it in different ways. On the next slide, I'm going to describe how the FB3000 works, but in general, the classes define how data gets from the real-time to an event. One thing to note about this whole mechanism classes, it's always possible to request all the events in any one of those classes with a single short DNP3 message, and then in return, you will get all the changes that have occurred for that class for all points. You can see that's a very efficient way of collecting data because you're getting all the data, but only the changes that you needed, only the important information. You don't have to poll every few seconds to get data with a second resolution, which is where the classes come in. So this is a screen capture of SBX Connect. This is the tool that you use for configuring the RTU. And if you're going to use the FB3000 with DNP3 and you want to have events, the very first thing you need to do, highlighted as step 1 there, is you'll see that for group 2, group 32, and group 22, you need to specify a scan period. By default, they're 0. What that is, obviously, well, not obviously if you look in the list, group 2 is binary inputs, group 32 are analog inputs, and group 22 are counters, like pulse counters. So for each of those, you specify a scan rate in seconds. So by default, they're all 0, as shown there. If you have them as 0, that means no DNP3 events will be created at all. So let's say you wanted to examine your real-time values every 5 seconds to see if they were changing. You would put 5 in group 32 for the analog inputs. That would be 5 for group 32. Having done that, the R2 will now be generating events. If you wish, the SCADA master, the DNP3 master, can just poll for those events and pull them back. Just say, give me all the events in class 0. Or, optionally, the FB3000 can send those unsolicited direct to the server, so it doesn't even need a request. If you want to have the unsolicited messaging, you need to enable it, where that radio button is pointed to by step 2. If you leave that disabled, it's important, as I mentioned, you can still poll for events, but they won't be sent to you by exception. If you want unsolicited messages, enable it. Then for each of class 1, 2, and 3, you have to individually enable those classes because you may only want one of the classes, right? Also, you should specify a maximum delay for each class. And let me explain. This is a way of making it more efficient. Let's say you're looking at your binary inputs. Nothing has happened for hours. There will have been no events, so there will be no need for any communications. But suddenly a valve opens, so you have a binary input change. That will create an event. Now, you may think the RTU should just instantly transmit that to the host, but it may be that there's a whole bunch of other stuff going on out on your wellhead, so there's some other data coming. So you can tell the RTU to wait for a period of time, in this case, 5,000 milliseconds. And what it will do is it will keep that event in a buffer in the RTU, see if any other events get logged, and if they do, it will send them all in one message to the server, which obviously reduces your bandwidth. It does give you a very slight delay on when the change is transmitted to the server, but remember, it has a timestamp associated with it, so when you look at it in the historian on your SCADA server or on a trend, it will actually be shown at the correct time it occurred. So you put that maximum delay in really to make your communications more efficient and to batch up events into single DNP3 messages. Sorry, the delay. Max events, this is the maximum number of events to buffer internally before transmitting. So for example, if we've just put this 5-second delay in, if something really unusual is happening on the whale pad, we may have 100 events all happen at the same instant, almost, on the well pad. That kind of thing might cause memory problems or performance issues in the RTU, so you want to transmit them as soon as possible back up to the SCADA server also, so someone is aware of what's going on. So what you can say is if I have more than, say, 5 events queued or buffered in the RTU, don't even wait the 5 seconds, just send them straight out. And which is also a way of saving resources in the RTU. So you need to use the combination of max delay and max events to tune to whatever your load is in terms of data changes and what you want in terms of performance of the network. So I'm going to summarize the last few slides because this is very important to how DNP3 works. There are 2 ways of accessing data via DNP3 Point. The first way is to specify a group, a variation, and which point you want. So for example, group 32 will give you access to all the events on analog inputs. If you wanted those returned as double precision floating point numbers with a flag and with timestamps, you use variation 8. And the point you might want is point 56. And that example would give you all events that have occurred for analog input number 56, which I'll tell you is the second meter's mass flow rate. So that's how to access points, and DNP3 protocol requests lists of points in any message like that. Alternatively, you can access class events. So let's say we want all data events in class 2. Group 60, I've not mentioned that before, is the group that gives you read events for a whole class. And if I want to read class 2, the variation should be 3. The reason is the variation there specifies the format, which is actually the class that you're going to go, and you need to take one off it. Okay, so for example, when I request variation 3, it's actually class 2. So that would give me all the events that occurred for all points in class 2. So it's a lot more efficient. One little request gets me all that data back. Now, the next slide, I am not going to go through. As you can see, it's a little overwhelming, but anyone who's using the FB3000 may want to print this out and put it on the wall. This information is all in our standard documentation, but I've collated it in a single table. Forgive me, someone could mute themselves. It sounds like you got a nasty cough there. So this shows all of the point types, all of the groups, and all of the variations that are supported by the FB3000. As I mentioned, this information is all in the documentation, but all I've done here is collate it onto a single table. And hopefully with the slides we've gone through, this makes sense to you. So everything I've described so far is accessing data points in the RTU. Sometimes you need to access more structured data, and I'm assuming that most of the customers on the call today are involved in the oil and gas industry, so you're probably familiar with electronic flow measurement data. That's data that's not strictly point-based, it's more tabular, usually. DNP3, the standard, allows access to files that are held in the outstation. And the FB3000 uses these files to provide access to tabular data. The protocol actually allows the DNP3 master to read, write, delete, and even to browse for files that are held on the RTU. In order to support the functionality that our customers need in the oil and gas business, we've added 24 file formats to the device, and they're documented. I'm going to describe what some of these do, but it's important to realize some of them do require the RTU's license to use the feature or to access the documentation for it. And these files fall into several different broad categories in terms of how you would use them. Okay, so we'll go through the first broad type is history. So that includes your regular daily history, hourly history, weekly history for all the meters and stations, and you do require a license for that. And that's equivalent to the data that you would have gotten history data points in a ROC, Enron, Modbus history, if you're familiar with it, or the archives for BSAP. The alarm files, those are they provide a list of alarms that have been detected included in the RTU. And it's a rich information. So, for example, it will include details of which alarm occurred, potentially a description for it, what the alarm limit that was exceeded was, what kind of alarm, all that extra information, something which you couldn't really simply put in a point. Events, these should not be confused with the events we've been talking about. These are API events. So, for example, a plate change on an orifice meter or a time sink that's occurred in the field. So these API events are put into a file, and then the SCADA software can collect it using DNP3. They're very similar to the BSAP event logs or ROC events, and normally these would end up in a FlowCal CFX file that's created by your SCADA system or your polling engine, wherever it goes. The next file type in there is mapping information. This provides information on the current DNP3 map. Now, you can see the map and manipulate it in FBX Connect, but we actually include some information on that mapping in files which are held internally in the RTU. You normally won't need to access those because you've got the tools. The next class of files are actually pretty proprietary, so we don't document them, but basically this is things like the RTU firmware, the load, diagnostics, things like that. And those go into the RTU, you can see they're there, which is useful because you can check the version and so on, but you can't read them. Finally, if you write an application that's either in C# or using the 1131 environment that runs on the RTU, that application can read and write files itself to the flash on the unit. Obviously, the content of those files is totally determined by you as a customer or a user doing that, but it gives you a lot of flexibility for storing information in files, for transferring it to the host. And it's worth mentioning that our partner, Vinson, have developed some applications. They have some standard files that go with those, and there's actually a folder on the RTU for each application that runs on the RTU, and the files are contained within those folders. So as a simple example, most of those applications have a CSV file that holds a list of all the user-defined tags that that application uses, which can be useful if you're trying to work out how to use it. There are some important things to realize about these files, though. Although the protocol defines how to read and write a file, it does not define the content of the file. That's defined by Emerson or by the end user if it's a user file. So as a result, a SCADA vendor, if they're going to use those files, must implement support to read and parse the files and convert them into their own format. Currently, as I prepare this presentation, Open Enterprise, that's Emerson SCADA system, Signet, and AutoSol can all read the history, alarm, and event files, though I would ask you to refer to their documentation, their particular product documentation, to determine the exact details, because it's a little bit of a moving target as people are adopting the FB3000. Another enhancement that you may have heard about if you've been talking to folks about the FB3000 is something called DNP3 tunneling. And there's a lot of confusion about this, and I wanted to try and clear that up today. DNP3 tunneling provides a mechanism for our configuration tools to access the FB series devices over a DNP3 port, a port that's being used for DNP3 communications. We've effectively come up with a mechanism whereby we've implemented a protocol within a protocol. And the way we've done it is DNP3 string, that's a point type, the string point type, with the index of 0, the SCADA master and the RTU can read and write to it. So they communicate by changing the value of that string. Now, the neat thing about this is it's fully compliant and compatible with the DNP3 protocol, because a string can always contain a sequence of up to 255 bytes. However, it's also completely transparent to any DNP3 master that doesn't support it or require it, except one thing you must remember is don't use the string 0 because it'll get overwritten if you put a value in it. The primary purpose of this tunneling, as I mentioned, is to provide FBX Connect with access to a functionality that isn't going to be required by third-party software. In fact, we might not want to provide that functionality to third parties, because it's okay. But it can also be used for direct access to the RTU's internal database. And something I want to say here, which is important, tunneling is absolutely not necessary for normal access to the DNP3 point data or the files, but it is used by our tools to configure and monitor the device. Currently, one other SCADA system, that's the AutoSol polling engine, supports DNP3 tunneling, but the only thing it uses for is it actually uses it to get direct access to some of the parameters that are held in the RTU database. All of the other SCADA systems that support the FB3000 use the native DNP3 groups and the DNP3 file transfers to communicate with the RTU and the flow computers. So, a summary slide. What have we learned today? I think the most important thing to realize, DNP3 is an industry standard. It's been very widely adopted across a broad range of utility industries. It actually started in the electrical industry, as I mentioned. The water industry in Europe and Australasia and Asia are adopting it as a standard across almost all utilities. It's published and it's open, and many customers are seeing it as a replacement to Modbus, and also a replacement for proprietary protocols, because proprietary protocols tend to tie you into one vendor. Using DNP3 can definitely reduce your implementation and maintenance costs, and also reduce project risk, because there's more access to information on the protocol, devices are more standard and more compatible. And finally, there's a very wide range of SCADA and polling engines out there that support DNP3. They support the standard DNP3 functions, and as I mentioned, you saw several of the SCADA vendors also support our Emerson file format now. And if you have, as a customer, a SCADA vendor who doesn't support our file format, please contact us. We'd be happy to talk to that vendor, provide details of the files, and encourage them to support those files as well. But even without the files, you can get the standard DNP3 point data and events from the device. And it's important to stress that. I'm about to open it up to see if we've got any questions. We may have time to answer one or two. But before I do that, I wanted to bring this slide up, and I'll leave it up as we answer any questions. These are some useful references. The first thing I'd say is the DNP3 Foundation is a user group that supports and writes the standard and takes input from users and vendors as to how to move forward. And they're at www.dnp3.org. There's actually a free primer document describing DNP3, going into a little more detail than I have today, which they have available at their website. If you search on Google for DNP3 primer, you'll find it. Also, the IEE, IEEE, also have the complete standard available. They should tell you that you have to purchase that. I think it's about $200, $200 or $300. So it's not excessive, but that gives you the full specification, which is very well written. It's pretty long. It's nearly 1,000 pages. Emerson also provides documentation. I've tried to show you some of that as we went through this today. The protocol manual, we've made available online for others to access it because we want people to be using the device. So that's out there at that URL, which hopefully you may screen capture if you want it, or I'm not sure if Quinn may distribute afterwards. Also, the documentation for the configuration tools is important, useful. That's changing a lot as we go through each release. So the best place to get that is on SupportNet, and I hope you are all registered members of SupportNet. It's free for the basic support. You can get access to that documentation. Then finally, third party. Some of this is written by folks selling, you might view even as our competition. But because DNP3 is an open standard, everyone has a lot to contribute to it. And I actually felt both the GE and the Novatech tutorials were pretty good. And there's some YouTube, hey, have a beer this evening and watch those. They're actually pretty good. And then there's also a really good comparison and a discussion by a guy who works in the field comparing Modbus and DNP3. If you search for SCADA dude out there on YouTube, you'll find that.